So in the last section, we talked about, what is calculus? It's a study of continuous change, and we related that to the slope of the tangent line, which represents the change of a curve at a given point, right? So again, going back to that mountain example, let's say there's some kind of mountain right here, and you're this little person right here. If you want to figure out how fast the height or the altitude of the mountain is changing, you could find the slope of the tangent at that point, and that will tell you how fast it's changing. Now, it turns out that rates of change is a very, very important relationship in real life, okay? So a lot of real-world relationships can be described by functions, and we want to look at the rate of change of these functions, okay? So the function y equals f at x, just a quick reminder, x is called the independent variable because you can put in any value of x independent of what the function value y is. And y, or f, is the dependent variable because it changes depending on what independent variable you put in. So if you put in x equals 1, you get a certain value. If you put in x equals 2, you get a certain value. So the y or the f changes depending on the x, okay? Now, how quickly this dependent variable changes, meaning how quickly your y or f changes, when there is a change in the independent variable, this is called the rate of change. Okay, so for example, how quickly you're moving along the x-axis will dictate how quickly the y value or the height of the mountain is changing. So if you're walking really, really slow, then the height isn't changing that fast. But if you're running up this mountain, then the height is changing really fast as you go, right? So that is the rate of change. Now, there are two main types of rate of change that you need to know for this course and in university as well. This is called the average rate of change and the instantaneous rate of change. Let's talk about the average rate of change first. Okay, the average rate of change, we can relate that to slopes. The average rate of change between 2 points, x equals a and x equals b, is the slope of the secant line of the curve between those 2 points. So if I have a curve like this, let's say it looks like that. And I want to look at the change between this point A and this point B over here, let's say. Then I can draw a secant line between these two, so a straight line that connects these two. And if I look at the slope, I will be able to tell on average, going from A to B, what is my rate of change? Meaning, what is the slope? What's my rise? What's my run? So this is the formula, essentially, for the average rate of change. You're looking at y2 minus y1 over x2 minus x1. Or you can think of it as the change in y, your dependent variable, divided by the change in x, your independent variable, okay? And in function notation, if you're changing from the point A to point B, it's f of b minus f of a divided by b minus a. Now, average rate of change is cool because that's a secant line, but it's not telling me the whole picture. For example, let's say I want to find the average rate of change between here and here. Then if I look at it, okay, if I draw the secant line, it's flat, so the slope is actually 0. So it seems like the average rate of change is 0. So someone who doesn't know the whole picture might think, oh, from point A to point B, you haven't moved. You haven't gone up the mountain at all. But that's not true because if I'm this little person, to go from point A to point B, I have to go up the mountain and then down the mountain. On average, the rate of change in which the mountain height is changing is 0. Yes, point A and point B are at the same height. On average, I didn't change the height. But essentially what's happening is the height did change. I went up the mountain and then down the mountain, but the average rate didn't change. So now we need to introduce a new concept called the instantaneous rate of change. So at any particular point, so let's say at this point here, or at this point here, or at this point here, at any particular point along the curve, if I just take the even smallest step forward, the smallest change in my x value, what result is there in my change in my y? That's the instantaneous rate of change, okay? Any small change in my x, any small change in my independent variable results in a rate of change. That rate of change is the instantaneous rate of change, okay? So we can relate that to slope again. The instantaneous rate of change at a point x equals a is the slope of the tangent line at the curve at the point x equals a. In the previous section, we talked about slope of the tangent line, and that is calculated using this formula. So it's no surprise that the instantaneous rate of change is calculated using this formula. Now in grade 12, when it comes to rate of change, you will encounter a lot of application word problems. Here are some common ones that a lot of students will see. First of all, you have velocity problems. What is velocity? Is that a dinosaur? Not quite. It's actually a speed with a direction. So think of it like speed, okay? For example, you're driving on the highway at 50 kilometers an hour heading east, or a plane is flying at 350 kilometers an hour heading northwest, okay? That's a velocity. So the velocity could also be thought of as the rate of change of the position relative to the initial position. So velocity could be seen as the rate of change, so the change in your position, divided by the change in time. Okay? Some questions will also involve cost, revenue, or profit. And just a quick reminder, the relationship between these three terms is that profit is revenue minus cost. Okay? Volume and surface area. A lot of times the rate of change of volume is related to surface area. I should say related here because sometimes it's not exactly, it'll differ by a constant, but usually the rate of change is highly related to the surface area.